So good morning to all the panel and to all the audience. So this is the final presentation about my PhD work that I've done these 3.5 years. And the title I decided to give to the overall work is Laser-Based Synthesis of Nanostructures for Water Electrolysis and Sensing Materials. So let's start from the beginning of my journey. It started everything in Catania, where but I had also the chance to travel a bit through Europe, presenting the work on international conferences, and then spending 6 months as an internship period in Barcelona. But all these cities, all this map has in common the key point of my work, the technique I've been studying and exploiting, that is pulsed laser ablation in liquid. From this, I will start my presentation, giving more detail, advantages, and main application. At first, I focus my work on the production of, let's say, easy nanoparticles that they've been employed for water electrolysis as water electrolysis material. But then the last two chapters, let's say, of this presentation, also my PhD, were involved on seeing two more novel aspects, say, of laser ablation. So the possibility of induced carbidization and producing transition metal carbides, for example, and the possibility to obtain in situ functionalized nanoparticles for biosensing application. Let's start from the king of this presentation. So the technique, pulsed laser ablation in liquid. This is what you will actually hear in a common day of synthesis, in which the laser is hitting well, you cannot hear the sound, but it's perfect. So this is the lab, and what is occurring is a laser hitting a beaker, in which you see immersed a metallic target, typically onto a liquid. From here, you should be able to see 10 shots per second. Those are the shock waves that the laser are producing, let's say, attacking the target material. But we want to resolve the scale, the time of the overall process. And considering the duration of the pulse of 10 nanoseconds, you will have this. So at first, the laser interacts with the metallic target. It is absorbed, the energy, and the electronic system is starting to be excited. This would be actually key. While the laser keeps going, let's say, onto the target surface, also the lattice is starting to be heated due to the long time of the pulse, and all the amount of energy provided by the laser will start, of course, the disintegration of the lattice material, inducing basically the melting and then the vaporization and ionization of the metal atoms. This will actually form a plasma plume. In a small area of like 1 millimeter square, you will reach actually high temperatures such as thousands of kelvins and gigapascal. This plasma plume actually will start, of course, a process of heat transfer through the surrounded liquid that is going to be vaporized under the heating effect, and a cavitation bubble will be formed. This cavitation bubble can be considered actually the reactor, the main point in which chemistry occurs and in which the liquid molecules interacts with the atoms coming from the metallic target, and here the nucleation and the growth of the final nanoparticles dispersional sheet will occur. Well, what about the influential factors of this technique? You have seen laser, we can have different effects if we manage the wavelength of the time pulse. Of course, the interplay among the target material and the liquid is crucial for the compounds. Actually, this is one of the advantages. We can have access to a wide library of compounds and structures that can be obtained through laser ablation in liquid. And the process, let's say, for example, the ablation time can be a parameter set in the field of the technique. Also, typically, these nanoparticles are pure nanocrystals, and we consider the technique quite limited ways, if we want, and cost-effective. Actually, the nanoparticle dispersion obtained are ready to use. Typically, we don't need any further washing or post-treatment, and as we don't need any further equipment supplying high temperature or low pressure, I mean, these can be considered a cost-effective side of the laser ablation. But given to the application that people have found about these nanoparticles, people have widely investigated the plasmonic application effect, for example, of silver or gold nanoparticles. Also, these nanoparticles have found application also in water treatment. They have shown antibacterial effects. Or magnetic nanoparticles have been actually synthesized and used, for example, as contrast agent in nuclear magnetic resonance, so biotechnology, and the typical ligand-free surface of those nanoparticles have made them suitable for catalytic application. Let's go further with the core of this presentation. So during my PhD, I've been mainly focused attention on the interplay among these three elements: the laser, the target, and the liquid. So actually, at first, I focused the attention on simple, let's say, ablation, because choosing to obtain and transition metal and oxides materials, and exploiting a bit some laser parameters. But then I went further in order to manage more the possibility and the combination among different target material and, for example, organic solvent, and open the route, let's say, to use carbonization and say carbides material. And finally, the use of molecules, specific molecules in the liquid could actually allow us to obtain functionalized nanoparticles for biosensing application, as an example. But let's start from the first point. So transition metal and oxides. These are quite nice materials, suitable materials for electrochemical water splitting. And when we speak about this phenomena, this is actually the most green approach to produce green hydrogen. So this water splitting reaction is the one that allows us to obtain hydrogen gas. And it occurs into these two half cell electrochemical system. And it typically we have two electrodes. So at the anode, we will have the oxygen production, while at the cathode, the hydrogen evolution will take place. This, of course, can occur in acidic or alkaline or neutral electrolyte, with all the further discussion about this. But if we would have actually an ideal electrocatalyst material, the minimum energy to provide the water splitting reaction is 1.23 volt. But as we are not dealing with ideal electrocatalysts, I mean, but real materials, what we will have is actually, say, of course, these are the current voltage curves obtained similarly for the anode and the cathode. And ideally, we would like to minimize the potential at which a specific current density is achieved. In this particular case, 10 milliamps per centimeter square will be chosen. But there's a consideration to be done. That's we can provide and use more material to provide more electrocatalyst active sites to lower the overpotential. That is actually the extra amount of energy to provide to the two half cell. But actually, this is a bubble plot presented by Kipska in a Nature Energy Research article. So each electrocatalyst performance is represented by a circle proportional to the catalyst loading used. And we have here the overpotential that, of course, we want to be as minimum as possible. But we would like to have also an efficient use of the resources in our electrochemical system. So highly desired would be the enhancement or the electrocatalyst intrinsic activity. Why? We want actually mass activity to be actually an index of the intrinsic activity of the electrocatalyst to be as high as possible, which would mean, let's say, provide also use less catalyst amount in order to be able to reach actually also lower overpotential. So this is, let's say, the main point and the main goal that community working in this field is aimed to reach, and also our goal. In particular, regarding our goal, the aim is also not only to obtain an electrocatalyst material using laser ablation in liquid, and also avoid the use of those critical raw materials, such as iridium and ruthenium, that are actually the most used and most well-performing. And this open, let's say, the road to the first chapter. So using PLAL to obtain as a suitable technique to obtain this electrocatalyst material. Transition methods, I said. So actually, the first years, let's say, of my PhD were involved about the exploitation of what happens when I use a nickel target immersed in water, and those are the laser technique features of use. So we are dealing with a nanosecond pulsar laser and using the ear wavelength. This actually first activity allowed me to exploit some laser parameters effect on the morphology and composition of the nanoparticles. So let's see. The point, the aspect I will focus on would be the ablation time and the fluence. The first one, as said, actually can affect the yield of the technique, and I've seen actually that by increasing the ablation time from 2 to 20 minutes, by high, you can see that the nanoparticle dispersion is going to become darker. In this case, is index, let's say, of an increased ablated mass. So by measuring the mass of the target ablated at the end and of course before the ablation. So this is a yield, let's say, parameter. But most curious was the study of the laser fluence effect. What is laser fluence? It is actually an index of the energy density. It can be estimated by dividing the energy per pulse provided by the laser over the area of what? Of the laser crater. This is the laser spot left by the laser interaction onto the nickel target. So by managing the distance from the convex lens to the target material, I tune, let's say, 3 main laser fluence values. You cannot maybe easily see, but the nanoparticle dispersion is becoming darker, and actually I checked an increase in the productivity, let's say, in the amount of material produced. But most importantly, the morphology is also affected by this parameter. We obtain spherical nanoparticles, and actually TM allowed to derive a nanoparticle size distribution that, in the case of high fluence, is broader and actually shifted toward a larger mean most representative size, you say. While lower fluence actually make us to obtain a more narrow size distribution and a lower size. So this can be actually further exploited as a tunable properties for the size of the nanoparticles. But going to the structures and the compositional properties of these nanoparticles, they seems to be actually core shell by the SEM measurement. And actually, by performing X-ray D, we see the presence of both the nickel metallic phase and the nickel oxide phase. Investigating the surface by means of X-ray spectroscopy, we see the presence of nickel oxide. So we can actually schematize the nanoparticles as displayed here. So having a nickel core surrounded by a nickel oxide shell, and then the hydroxide, as they actually also obtained in water, at the very edge. This is actually a highly reported material as oxygen emulsion reaction electrocatalyst. So let's go further on realizing my electrochemical cell. I had to realize a working electrode, so I choose to drop some nanoparticle dispersion onto a carbon-based substrate. And now two questions came. That is, how the nanoparticle distributes over the drop area, and how can I estimate the catalyst loading, because it actually wasn't so easy using a microbalance. So in here I use Rutherford scattering spectrometry technique. This consists of an accelerated helium ions beam that interact in this vacuum chamber with our sample material, and the energy of the helium ions backscattered is collected. This is a typical example of the sample order. Of course, different elements are backscattered with different, say, energy. So I could see, for example, the presence of the carbon signal related to the substrate, the oxygen, and nickel. And what is useful for us to determine the nickel distribution and the catalyst loading value is the area underneath to the element P, in this case the nickel, that is actually the dose, so atoms per centimeter square. So if I sampled the example, the drop area in different points, and I obtain these nickel dose distributed, let's say, in the drop area, stating a quite homogeneity in the distribution of the nickel phase. Moreover, I went through the electrochemical measurement in alkaline environment. So this is the electrochemical cell used to study this kind of this working electrode. And what was happy to see is that by performing linear speed voltammetry, the current actually, the 10 milliamps per centimeter square, for example, current density, was achieved at a lower potential using the substrate loaded with the specific amount of nickel oxide nanoparticles, proving the catalytic activity of these. But as said before, I'm not only interested to the extrinsic activity of the catalyst, so the recovery potential, but also to the intrinsic activity. And in this, the catalyst loading has needed to be evaluated. So the three RBS spectra were analyzed, the dose of nickel was derived, and actually you can see how low the catalyst loading is. Allow me to obtain high values of mass activity, so the order of 10 ampere over milligram. If I compare this value in the bubble plot shown before, but focusing with the comparison with other nickel oxide, hydroxide, electrocatalyst material, actually the nanoparticles obtained achieve a quite lower competitive potential value at the same condition, of course, but most important, the high mass activity was achieved compared to those common chemical-based synthesis approach. So with this first part, I want to show you actually how easier, actually versatile PLAL is for nickel oxide nanoparticles synthesis, the effect of laser fluence, for example, on those nanoparticle features, and how I was able to achieve a very good performing electrocatalyst material for the OER. You will wonder now, what about the cathode reaction if we think about the two-half reaction? So HER is actually the, let's say, the most important side of the cell producing actually hydrogen. It is a quite fast, let's say, in acidic condition due to the presence of H protons in the electrolyte. But in the case of alkaline, we need a further step in the overall mechanism of H2 production. So people are highly struggling on finding how to accelerate and obtain this reaction at lower overpotential, for example. The best catalyst material used for this reaction is actually represented by platinum. We cannot fight with this, although actually platinum is quite critical material. If you check on several critical material assessment, the platinum group metals are one of those by highly critical due to their high importance to energy and also higher supply risk. That's why actually we need an alternative materials. And transition metal carbides seem to be quite efficient electrocatalysts also for this reaction compared to platinum, not the same performance although. But I want to focus on molybdenum carbide. Molybdenum carbide, actually, I first met, let's say, this material in this research article in which they carbonize the molybdenum substrate by using a high temperature molten salt reaction. And so this is one of the features that you will encounter if you look for way approaches of obtaining transition metal carbides. You typically see long time lasting operation and high temperature. But what actually catch my attention is the performance that this material can provide for HER in a same environment. That also in higher current density, the potential needed to achieve a specific current density actually are lower than the platinum foil. So this makes this material widely interesting for HER. Also, let's say, managing the phase control can allow to, let's say, get a more proper, let's say, combination for the hydrogen energy formation. But the question is how I can obtain carbide using PLAL. The answer is, this is the start of the second, say, paragraph chapter. It's on using a metallic target, in this case molybdenum, and providing carbon by using an organic solvent. In this case, ethanol was chosen. In this reactor, basically, we will have that the molybdenum ions actually ionized coming from the target will interact with actually the carbon, the molecules of ethanol that are dissociated in this actually high stream condition, and the carbon can be included and solubilized in the molybdenum structures, allowing the production of molybdenum carbide. This is what I've done, so using ethanol and a molybdenum-based target, and those nanoparticles obtained were spherical, having a mean size of 10 nanometers, and agglomerated to quite nice distribution, let's say. But most importantly, in ICN2, where I also spent my 6 months, actually, I had the chance to perform, actually, to deal with the measurement of TEM analysis, not done by myself, 300 person. But in here, what is important to see is the presence of both carbon and molybdenum within the same nanoparticles. But we are also interested to see which is the phase, carbon phase obtained, MOC or MO2C. They are both present in this case, and we have by high resolution TEM and also X-ray diffraction technique, we can see the presence of cubic molybdenum carbide and hexagonal molybdenum carbide. So this is, a proof of obtaining both the two materials. So this motivated me actually to go further with the electrochemical test. In this case, I decided to load the nanoparticles into a nickel highly porous substrate. And here, the LSB curves show us the reduced the reduced potential needed to reach not only 10 milliamps but also higher current density when the nanoparticles are loaded onto the substrate. We cannot avoid to compare this result with the most commercial benchmarks. First of all, platinum-based material represented by these blue spheres. Actually, it has high mass activity, so it's under low potentials. We cannot fight with this. But what is interesting is that the materials obtained by PLAL still shows a good high mass activity, competitive to those of other platinum-based electrocatalysts, and also compared to the other molybdenum carbide obtained by those harsh, let's say, synthesis approach, the potential but also mass activity obtained are quite competitive, not only at 10 milliamps per centimeter squared, but also at higher current density. So although the HER performance are still, let's say, open to several optimizations, the point in this part was to achieve the successful production of molybdenum carbide nanoparticles and provide them a characterization for HER in our current environment to prove PLAL as valuable technique for this material synthesis. So let's go to the last part of this presentation, the possibility to achieve functionalized nanoparticles. Why we will need functionalized nanoparticles? Typically, community is functionalizing nanoparticles to prevent their agglomeration, for example, or to control the shape of the nanomaterials that can be actually obtained. But in our case, the aim was to provide to the surface of the nanoparticles functional groups that can make these nanoparticles suitable for biosensing applications. Which kind of which was the biosensing, let's say, goal. In this case, the attention focused on alpha-synuclein. Alpha-synuclein is a protein that, especially in neurons, can, if present with higher concentration, it tends to aggregate and form Lewis bulb that can then induce neurological disease. That's why the presence in high concentration of this protein in cerebrospinal fluid, for example, but also in other media, it is correlated generally to the presence of Parkinson's disease. Where to detect, as said, cerebrospinal fluid is a medium in which we can find and detect this protein, although this would mean a quite invasive detection. That's why we will focus, the aim is to focus on its detection in more easy and point-of-care solution and accessible media such as plasma, saliva, and steam. In the case of plasma, the concentrations are quite low, picograms over ml, and another challenge is actually to be able to have a biosensor that can actually discriminate the values of Parkinson's disease patient toward the one of an healthy patient. They're quite challenging. Which kind of detection method of sensor we can use? So the ELISA assay is actually the most established one, the more precise, although it needs quite operators and long time. That's why the other three solutions, so for example, electrochemical based sensor, has been chosen as more suitable for point of care detection of these protein and not all in general for biosensing community. And in this, of course, we need a properly functionalized surface. How we can functionalize, for example, the surface of nanoparticles. Typically, ex situ approaches are used. So we first synthesize nanoparticles, then the materials is exposed to a proper functionalization environment. And this we actually need several steps and time and process. But what we aim and what I aim to show in this last part of the presentation is the possibility of obtaining in situ functionalized nanoparticles by using laser ablation ability. So during the synthesis, but also the functionalization of the nanoparticles. How? Well, to achieve this point, I included in the ablation environment, liquid environment, the presence of a molecule, glutamic acid, that is interesting for the presence of carboxyl groups. You can see already, and I performed the ablation of copper target in this case. You can see the difference by eye. Let's say these are dark, let's say red, let's say this is brownish dispersion, while the obtained dispersion with the presence of GA also appears with a different color, index of something is changing. Well, for sure, by the morphological point of view, you can see difference in the morphology, although from the ECM, you can see a presence of polymer material that embed the nanoparticles. But most interesting measurement analysis was the one performed by X-ray photoelectron spectroscopy, so XPS. First of all, seeing the effect of the GA presence in the oxidation state of copper. That is actually reduced the oxidation state of copper with the presence of GA. You can see not the presence of shake-up. So let's say you have cuprous oxide shell instead of cupric space. But most important was the nitrogen signal. In the presence, let's say for the sample obtained in methanol, we have that this thing can be deconvoluted actually in two mentioned points. The first one, the more intense, unfortunately, is the one related to the presence of protonated amine groups. That is actually correlated to the presence of unreacted GA. But the part that is interesting for us is this shoulder that can be related to an effective bond among the metal and an amine group. Moreover, in the deionized water, this peak seems to be centered more on the presence of only bonding in amine group. That's also actually deionized water provide a higher solubility toward, let's say, GA. So this made us, let's say, to give a proof of the functionalization of the nanoparticles obtained. In this way, we went further to the sensor realization. So we decided to take a flexible substrate, conductive one, which we loaded nanoparticles, and then we activated the carboxylic groups presence on the GA that allowed the functionalization with the antibody, then the blocking agent to block the unspecific bonding, and then finally we exposed the sensor with specific protein concentration. But how all these steps provide us, let's say, a measurable signal? So if we consider the measurement, electrochemical measurement, in this case a cyclic voltammetry of heat of death, in a redox probe, we use a ferric ferrocyanide species, in which, of course, we know that iron is going toward oxidation and reduction in a reversible way. So we have the presence of the two peaks of index of the presence of this electron transfer. When I loaded the nanoparticles onto the substrate, I observed the current peak to be decreasing in intensity. And going further with all the functionalization steps, this peak was slightly shifted and also the current decrease. What is actually occurring at the surface of the electrode? So the ferrocyanide pieces need to undergo a series of oxidation and reduction. But we have here, of course, our nanoparticles with all the further functionalization steps, antibody, the protein, or the DSA. This is actually can be schematized using this equivalent circuit, in which the most interesting part is this actually proximity of the electrode, in which the charge transfer resistance can be studied and investigated by the using of electrochemical impedance spectroscopy. And that's what actually made us to have to achieve a more resolution, say, to see better what is occurring. So by going further with all the functionalization steps, this charge transfer resistance is going to increase. Why? Because we are providing less and less accessible sites through which the ferrocyanide oxidation reduction can occur. So this lead to the increasing of charge transfer resistance. Most importantly, we are focused on this difference. So the difference among the BSA step and the protein exposure. In this case, so this allows us, this kind of measurement, to provide, let's say, to report the incremental variation of the charge transfer resistance at specific concentration of the proteins. In particular, we started with 50 microliters of methanol obtained GA-rich solution, and I was only able to see a difference in the ERS only at 1 nanogram over ml of protein. But increasing the amount of dispersion, thus nanoparticles, to the sensor surface, I was able to see also to lower, say, my detection limit to 10 picogram over ml. Moreover, by using, the same amount of nanoparticle dispersion, but using the water-based obtained dispersion, the sensitivity improved notably. So still, we wasn't able to see any difference in the charge transfer resistance at 1 picogram over ml, but the sensitivity improved a lot. So although further evaluation can and needed to be done for the biosensing part, the aim and focus on this part of my work was actually to achieve the functionalization of copper nanoparticles in situ and the exploitation of GA as possible molecule for providing the proper surface functionalized for alpha-synuclein biosensor development. So with this, I'm going to move towards some conclusion. And the start with laser ablation was not so easy, because I had to deal with some cooling system issues related problems. But then the first bios were obtained. And in here, we decided to focus through different materials. And specifically, what you're seeing today is the subsequent synthesis of nickel oxide nanoparticles that allowed me to study at first some laser parameters effect, and moreover, the possibility of test them as efficient, actually, electrocatalyst material for oxygen evolution reaction. But by changing the target material and using an organic solvent, I was able to achieve the formation of carbide materials, quite interesting and innovative materials for HER. Luckily, no one has first tested this kind of nanoparticles produced by PLAL for HER. And also, and finally, the possibility of still engineering, let's say, the liquid environment in which the ablation is occurring in the presence of a specific molecule that can open the route to a further development of a biosensor. So specifically the in situ functionalization of nanoparticles. And with this, I had the honor to be awarded with some prize during all this path, but most importantly, also some research articles were born, let's say. Not only the copper nanoparticles were also used in other fields, such as in order to improve the light adversity in solar cells, or for example, the realization of a gas sensor, in this case, a chemoresistive sensor for nitric oxide. And with this, I want to acknowledge of the institution that have actually supported this work, the CNRMM, the Biotech Research Innovation Tower for the X-ray, D, and XPS measurement, the ICN2 for the EM measurement, and also the warm welcome and the internship period in the Nano Bioelectronic Biosensor Group, the DFM team, DFA team, and the projects such as Samotrace and the Image project, in which I am involved as research fellow from the August of this year, still working actually on innovative non-critical raw materials for green hydrogen. And finally, of course, the PhD coordinator, Shur Compagnini, due to its wide coordination of my cycle, the PhD cycle, my supervisor for their constant guide and support, because without them, this won't be pretty possible. And in here, of course, all the friends and the second family I have achieved. So, of course, you for your attention in this 40 minutes.